Okay, good morning. So, what we will do today is an important class which is hardly taught in chemistry departments, at least nowhere in India in chemistry department it is taught, and so I insisted that this should be dealt in very elementary form and in detail. And in the book, StatMac book, there I have devoted 5 chapters of 30 to 5 chapters. So, that kind of tells you how much importance I give to the phase transition. As I told in the last class when we did the Mayer's theory, so Mayer's theory is one of those 5 chapters. In Mayer's theory, Mayer was the first to do a theory starting from interaction. As I told you, ideal gases don't have a phase transition. Ideal gases don't become liquid, they don't become crystal. They are in good reference systems, but they cannot explain the real world. What you and me exist and the phase transition happen because of molecules and atoms interact. And one of the most dramatic consequences of the molecules interact is the phase transition. And however, the understanding of phase transition is very tricky because the concepts are profound and deep. And many of the things that we know in physical chemistry and physics, even chemical kinetics, and as far field as chemical kinetics are derived from the basic idea that phase transition gave to us. For example, concept of autoparameter, concept of free energy landscape, the glass transition, ruggedness, all the things that we hear or multidimensional processes. Many of these things have their origin in this is beautiful and the very profound and fundamental field of phase transition. Okay. So, this what we will be doing, though it is a Landau phase transition, it will be lot more. So, the main theory of this. So, in 1937, do you know this great Big Bang episode that when Penny Sheldon was teaching Penny physics, and the one warm summer evening in Greece. I suddenly remembered what I am going to say reminded me of Big Bang theory. If you have not seen that particular episode, you should see that. It is really one of the most hilarious in Sheldon and Penny. Okay. Now, in 1937, much later than the Greece, there are 2 things happened in the same year. Joseph Mayer came out with the theory of condensation, and which went on, as I mentioned in the last class, our cluster concept of cluster expansion, representing interacting molecules as dots and lines between them, which gives to graph theoretical picture of physics that are ultimately developed into Feynman's integrals and all these things. The representation of an integral in theoretical physics as the graphs started with Joseph Mayer. Then it went on to become Mayer-Arcel cluster expansion in quantum mechanics. Okay, and of course, the Feynman's did in quantum electrodynamics, and we are talking of atoms and molecules and phase transitions. The same year, 1937, Landau came up with a theory of phase transition, which is extremely simple and elementary, but it captures very essence of many of the things that we will be talking today. But before I can do that, I will try to go through some very basics, as I said, because the generality of phase transition is not what a chemist usually used to see. We are used to specific properties of atoms and molecules that attract us. So, when it comes to thinking generally and general picture, this is not something that is our forte. Okay, so I will have many elementary concept basics chapters that will be there. You can just quickly read, or I can read, but they will be not spending too much time on that. That is ubiquitous in late nature, it is manifested in a large expanded detector. Main thing is that there is a infinitesimal change in a control parameter like temperature, pressure, or which will be our outer parameter. I will talk about it later. Infinitesimal change leads to a macroscopic change or thermodynamic change. So, remember the concept of derivative. You put the change of your dependent variable in the numerator and your independent variable in the denominator. So we always think of change in terms of a derivative. So you can easily see, if I have an infinitely small change in a control parameter and I have a macroscopic thermodynamic change, then that means we are talking essentially of a very peculiar phenomena, which is called singularity. See, much of the things that you read in your calculus are the ones with the functions that are called entire functions, or their first or second derivatives exist. So that is how we work with them. If you have a singularity, you cannot do anything. So that is the first difficulty we will have. So it is many branches of natural and biological science, like of late we have the protein folding, that is completely used the language of glass transition and the folding funnel, Bonucci covalence, all these things are just completely borrowed from phase transition. Or nowadays in many of the things in genomic studies and all this again from phase transition. So it is a discipline by its own merit with entire books devoted to phase transition, like the book by Eugene Stanley is on phase transition, then there is one by Balescu. There are many books just on phase transition by itself. And I find people, I disdain people who do not find it interesting, very frankly. This is such a beautiful subject. Okay, it is a strong language, but I think sometimes you need this strong language, at least in India. So this is amazing, there is different diverse types of phase transition that we encounter in nature, yet there is an amazing unity in such diversity. These are all lines from my my own textbook and my own writing. Okay. Among all this, there is a unifying property among all the different kinds of phase transition is the nature of discontinuity. So I can characterize a huge number of phase transitions by saying that whether it is a first order or second order. As soon as I say it is a first order, then there is a huge number of phase transitions which immediately become a, that they are certain characteristics which are common or universal. When I say second order phase transition, again a huge number of phase transitions can be grouped together. So this characterization of first or second order phase transition is possible, and that brings this the unity in diversity that I have been talking about. Okay, so depending if phase transition is categorized in different order, namely first order, second order, and classification is a grouping of phenomena in similar characteristics together, and a few of them, large number of phase transition observed, So what one is trying to do now, characterization, and it is very powerful. For example, when it is a first order phase transition, gas liquid phase transition, liquid to crystal phase transition, many other phase transitions, or magnetization, magnetic phase transition in the presence of a magnetic field, electrical transition in the presence of electric field, huge number of isotopic nematic phase transition, nematic smectic phase transition in liquid crystals, the huge number of things in polymer. As soon as I say it is a first order phase transition, they are all very similar. So I know what does mean by first order phase transition. Similarly, when I say second order phase transition, the order disorder type phase transition, gas liquid phase transition, critical point, and a huge number of transitions like that, which this. Now, so we started off saying the order. Now before that, I tell what is an order. Let me tell you, we need to know something to characterize the phase transition. This is done through a function or order parameter. It is a physical quantity so chosen that it is 0 before the phase transition, but becomes non-zero and acquires a finite value after the phase transition. That is the definition of order parameter, which is selected, which is chosen. For example, if I have a gas to liquid transition, then so the canonical gas liquid, we'll see it many times, pressure versus density. Then this is the, so this is gas, this is liquid, this is crystal solid, and this is so this is the coexistence. Now the order parameter at a given temperature will be this change in density. That means density here rho L minus rho gas, that will be order parameter. In a magnetic transition, it is a magnetization that will be the order parameter, because that is 0 before the magnetic transition, ferromagnetic transition, and non-zero afterwards. So these kind of identification is extremely important, and that was the one that was implemented by Landau, because this change that I'll be seeing here is which characterize. So the whole idea is that if I want to understand how a phase transition takes place and why a phase transition takes place, this why and how will depend, I see if my understanding is proper or not, whether I can explain this change in density. For example, typically let us say, as I described earlier, that one of the another unifying thing we do is we introduce rho star, that is n by v cube of molecular diameter. The universality comes because all the liquids have very narrow range of rho star. They may have very different number density, like 10 to the power 22 per cc, then they 10 to the power 23 per cc. But in that, when you take the molecular diameter, the number density and multiply, you find they are all between 0.8 and 0.9. This is wonderful. Then most of the gases, they are widely different, but at the condensation, typically not too quite a bit lower than critical temperature, but not too low. This is typically will be between 0.05 and 0.1. Let's say 0.1. So now I suddenly have a fantastic, whether carbon dioxide or methane or water, I have a fantastic, or methanol, a fantastic unification when I go to the dimensionless quantity. Now, as I was saying, I am just giving a number. This rho star is 0.1, and then liquid typically goes to 0.7 or 0.8. So, I have to, if I understand properly, I should be able to say why gas to liquid transition density increases by a factor of 7, okay, and what pressure it happens, and I have to be able to say what are the other characteristics of the change, like latent heat. So, these are the kind of properties that one would like to know. The whole this understanding of phase transition starts with the identifying an order parameter, which is, as I said, 0. So, if I did rho L minus rho G, so it is 0, order parameter 0 just before there, then it jumps by a large number. Okay. Now, this was the very famous classification by Ehrenfest. Ehrenfest introduced this, and this is the beginning. Order parameter and Ehrenfest classification is the beginning of our formal study of phase transition. So, Ehrenfest defined the following way. He noticed that gas liquid, liquid crystal, these two here, and as I said, magnetic transition in the presence of external magnetic field, all are characterized by finite change in a first order property. First order property means first derivative of free energy, like entropy, and then pressure, or other DADP, you can get the density. So, the first order properties change. Then he noticed that there are cases where it is a like superconductivity. It is the second order property that is changing. Order disorder transition in metallic alloys, it is the second order property, like this specific heat, the susceptibility. Specificity is second derivative of free energy. Susceptibility is second derivative with respect to volume. Okay. So, there is a class of phase transitions which are characterized by first discontinuity or singularity or anomaly in the first derivative of free energy, and their properties which are second derivative. And this is suddenly you begin to say, okay, then there are characteristics between liquid and pneumatic and spectic, or gas and liquid is all the same. Yes, they are all very similar, and we will see their similarity even more. They all have the latent heat. While the second order phase transition, they have no latent heat. This is very important. They have no latent heat. They have a discontinuity second order property. So, the Ehrenfest classification at one shot allowed us to classify very different kind of phase transition, which apparently so different, but they are similar. Okay. Again, motivation of the questions, I have said that these I have said, all various phases of solid, liquid, magnetic, include order disorder transition, metal insulator transition, superconducting transition, sol gel transition, liquid crystal, all these things. Now, one very important thing I should point out, that it is a field, simple intuitive arguments fail miserably. And this is one of the reason our the theories are held so so highly regarded. And I will say how it does not work. Like one of the most important thing is the second order phase transition is which was solved 1971 by K.G. Wilson by introducing the innovation group, which is one of the most formidable thing that has been created by our mental things, human beings, our intellectual feat. Now, so what we have to say, as I say always, why and how, why we study, I just said you, and what are the main characteristics of the phenomena, why does it occur in the first place. One would like to understand both from microscopics, is not here microscopics, and from macroscopics, both from fundamental and phenomenological point of view. So, there are many examples. I said, okay, let us go through them. Liquid solid, this is the one of the most common things we see everyday life, and the famous paper of come from India of T.V. Ramakrishnan-Yussouff Kanpur IIT, that one of the highly cited paper is the freezing transition. The first line of that beautiful paper was that freezing is the most ubiquitous of all the phase transitions. Great line they started with. Then parametric ferrometric phase transition, order disorder phase transition, binary mixture, large change of composition, normal superfluid transition, liquid helium, taking to superconductivity, superfluidity, then metal insulator transition, again change in resistivity, sol gel transition, helix coil transition, DNA protein folding, list goes on. No, very good question. Many of them are second order, like superconducting transition is second order. Superconducting is very unique. I'll talk about superconductivity little. Helix coil transition is a first order phase transition. Helix coil is a first order phase transition. Protein folding is considered also first order phase transition, and but the change is very small. Helix coil transition order parameter is we use the helical pitch. Yeah, exactly. And this theory, if you are interested, please take a note. It was done by Zeman-Bragg, 1959. 2 pages next to each other, both 1.5 page or even less than that, and other by my advisor Gibbs and DiMarzio and Julian Gibbs, and it's beautiful theory. The reason it becomes first order is very nice. See, as we will discuss, a second order phase transition, particularly order disorder, gas liquid at critical point, they are characterized by large scale fluctuations. And so huge density fluctuation near gas liquid transition. The compressibility goes to 0 in gas liquid transition. Order disorder transition, again your composition is hugely changing. That is the composition, that is the order parameter. That first order phase transitions are characterized by that you need a nucleation. That means it does not have, is not characterized by that kind of huge phase fluctuations. So, this is, so when helix coil transition takes place, if you want a DNA helix to be broken into coil, then you have to first break the 3 hydrogen bonds. You break the first hydrogen bond, you do not get. Second, you break the third one, then it starts rotating, you get the rotational entropy. Okay. So, that is the essential nucleation phenomena in that. Okay. We will not be able to understand everything today. In this one lecture, as I told you, full semester course is given on phase transition, but the idea here is to introduce the universality and the grandeur of the field and the concepts like order parameter, then first and second order phase transition, which I said that is the first and second it is determined by the derivative of the free energy where it becomes discontinuous. That means this is the Ehrenfest classification, the order pattern given by the first derivative of the free energy with respect to order parameter or other thing control parameter, that shows discontinuity. So, in second order phase transition, first order derivative like density, entropy, they are not discontinuous, but in the first order phase transition is the entropy, that is what we call latent heat, that is discontinuity. So, heat content entropy jumps, and from crystal to liquid entropy jumps, and entropy is the first derivative of free energy. That is why melting, freezing are first order phase transition. Okay. These I said is continuous change microscopic derivatives, finite change of a macroscopic variable caused by an infinitesimal change. These I said, but it is very important that infinitesimal change in a variable, but a macroscopic change in a variable is the hallmark of a phase transition. That is the uniqueness and the beauty of the phase transition. Okay, these are the many of these things. This is the famous temperature density plane. So, this is the vapor, this is the liquid, and this is the critical point, and this is the coexistence. All across coexistence we get a phase transition. Here we get condensation, here we get boiling, okay, and this is the coexistence between liquid and crystal, and here you get the phase transition. Lot of interesting things happen and lot of study going on now in the supercritical fluid. And you also know this, we asked in our interview, and about 80% students cannot answer any of them. I have done statistics. 80% of the student cannot put, they are coming for doing PhD. Pressure versus temperature plane they cannot do. You can ask this question here, it is very interesting. They will put solid here, liquid here, and so it is a kind of a Rubik's cube. We make them do, okay, but here is a first order phase transition, a liquid solid melting. Here sublimation is the first order phase transition, gas liquid is the first order phase transition, but it is only here, it is the, at the critical point nature of the transition changes, it becomes a second order phase transition. And that second order phase transition is like this. So, this I have drawn the van der Waals loop also to this is a Maxwell construction, pressure versus density you have seen in your first year undergraduate. And in the first year undergraduate books there is a great section which is called law of corresponding states. That is done in a huge way. Now, it is time for you to ask a question, what is the law of corresponding states and why it is so unique? Absolutely. This is our first in physical chemistry or physics, the first A with the universality, that I can P by Pc, V by Vc and T by Tc, and I get an equation from van der Waals, remember is on the right hand side 8 by 3R, and you get that equation now describes everything. Suddenly you get a master curve, you find when you plot a pressure versus density, everything is different. You cannot even plot them on the same graph paper because density is so different, pressure is so different. But suddenly when I plot P by Pc and V by Vc or rho by rho c, suddenly everything collapses, you get a master curve. When van der Waals did that, he of course knew, and van der Waals did enormous, as I mentioned once before, that he is one of the underrated scientists, his huge amount of work he has done. So, this law of corresponding states first told us that there is something very interesting, very fundamental going on. I do not have a slide on law of corresponding states, I should have had, but I forgot, okay. Now, then order parameter is chosen, physical quantity, as it's 0 before the transition becomes non-zero afterwards. So, and that provided by liquid solid transition, a clear example that we will go to. But here I have said entropy versus temperature, this is the first order phase transition. However, in a second order phase transition, it is, of course this is, but it is specific heat that diverges, all of us know that. There is only one truly second order phase transition in Ehrenfest sense, only one that we know, and that is the superconductivity. So, if entropy goes, there are a lot of things on that because this has to be a positive because ds dt is specific heat. Those are the things we will do a little bit. Then resistivity against temperature, this is the only is the superconductivity, but most of the second order phase transition, there are two, we call two kinds of phase transition, is a Ehrenfest sense, other one where lambda transition in superfluidity So, you guys have seen that, these figures, teachers, I think everywhere professors or whoever teach it or write books, they are all excited about this amazing thing that is here, and this itself has given rise to huge amount of theories, understanding, papers, Nobel Prizes is and as I said, is highly regarded. I happen to do my PhD start after a few years after Kenneth Wilson's famous Renaissance group calculations, and there is still so much excitement going on. And Leo Kadanoff, who started some of the things, was at Brown, and Leon Cooper, who did the superconductivity Cooper pair, was at Brown. So, it was a lot of fun to seeing the people who created physics around you. So, this is the example of a Ehrenfest first order phase transition, this one, Ehrenfest first order phase transition, Ehrenfest second order phase transition, this we call continuous transition, or Ehrenfest second order phase transition of the continuous type, that the little bit we do. As I said, some of the things will be elementary. I have to introduce people to the nomenclature. Okay. Now, one thing, as I said, I always teach, because this has come out from India, though the first one done by Kirkwood and Monroe in 1941, but that was not successful for reasons I cannot go here. But the first successful theory of melting, freezing, was done by Ramakrishnan-Yussouff in paper written in 1977, came out in 1979 in Physical Review. What they did, and I teach it because it is a wonderful example of order parameter. So, this is the density of the solid, which is inhomogeneous, position dependent density. Liquid is homogeneous, there is no position dependence, that is average density is rho L. If you have read Kittel or any solid state physics books, then the density of solid is written in an expansion where G is the reciprocal lattice vectors. So, when you do the X-ray, you get reflection of these planes, these are the sharp peaks. However, the solid will not show that unless this factor is in front. This is a phi G, this is the order parameter, that becomes non-zero when liquid becomes crystal. And phi naught is the fractional density change between liquid and crystal. Like when I go to liquid to water to ice, then this phi naught is negative. But most of the other cases, sodium and all other, this is our molecular liquids, this is positive because density increases. Phi naught and phi g are the one of the best examples of the order parameter. So, there are certain things given, a parameter magnetization, some other examples, gas to liquid density, as I said, rho L minus rho g, and liquid to crystal, then phi naught and phi g, and there is a bunch of them, because you have a bunch of reciprocal lattice vectors. In principle, you need to take all of them, but in practice we find couple of them. It describes the theory, and they get very good agreement with it. This is one of the most successful theories of phase transition. It is actually also called Landau theory, for reasons I will explain little bit. So, this is a very important slide where one gets examples of the order parameter. Now, I want to tell you, and if you can tell me, it will be even better, why we give so much importance on order parameter. So, this is again the same thing, a phase transition labeled by lowest derivative of the free energy with classifying, but then first order phase transition, continuous second order phase transition, true phase transition is superconducting transition is the true phase transition, is exceedingly rare. We know only one case. Okay. So, now some of the questions we need to ask, as I said, why and how. Why does a system undergo such a sharp change at a phase transition point? What is the origin of discontinuity? Can we evaluate the transition parameters such as these are the things I wrote today morning to make it really simple to bring home the point. Now, I have to ask you a question, like last question corresponding state was very good. Now, Kailash or somebody again tell me why we need order parameter. Well, one is of course the unification. one is order of a transition, then unity among diversity, all this beautiful stuff. But there is one technical reason why Landau made it or introduced it and made it so famous. There is a practical view. You know, the scientists are very pragmatic, practical people. Theoreticians are even more practical. They may go around with a air, they are not practical, but theoreticians are often very practical people, because we do what we can. Is acts as a control parameter, correct, but I am asking more.
We know about the order we can we know the
Yeah, that is a practical side. I am saying theoretically, Landau was a theoretician, he built this theory and he is the one who actually introduced all these things, the order parameters and all these things. Okay, the reason is that we do all these things, the reason is that we need to have a theory. Now let us think, we need to have a theory, and what do we really need for the theory? What is that this thing, or what is the question? What is the question? The question is that it reaches here, it goes over to liquid, or reaches 0 degree centigrade, a water in your refrigerator becomes ice. And so when I ask why, what exactly is that question why means? Why means that there are certain characteristics in this branch, certain characteristics which manifest itself, which kind of initiates or motivates the transition. Okay, one very simple answer you could give, and I expect you to give. What is the thermodynamic answer? Why water becomes ice? Absolutely. So free energy becomes minimum. So if the free energy is like that, then that is a coexistence, but when free energy goes down, then this will be T below 0 degree centigrade, and this will be ice, and this will be liquid water. So thermodynamic sense, we know the answer, that it is the free energy becomes low. And so that was one of the first thing that people know, and people knew it, I think, even in 19th century or 20th century. So this part is well understood, that a phase transition takes place when the free energy, the system finds that it is more profitable free energy wise to go over to the new phase. Okay, that is a valid and good answer. Now as I said here, why liquid sodium goes to BCC while argon goes to FCC? These are the kind of answer, if I want to know, then I have to look at the characteristics here, in this region that holds the key that it goes to BCC, sodium. Similarly, here is the characteristics that tells you how big the jump will be at a given pressure from gas to liquid. How do I describe that now? Okay, one of the thing is that I calculate the free energy here, I calculate the free energy there. Then I say, okay, I just what we did there, we compare the free energy, and both will have minimum, and then when this minimum goes down, then it system goes over to the this space. That is an explanation at a level which is macroscopic level, but we want to know a little bit more than that, and we also want to know why the certain universal characteristics emerge in these kind of things, and what allows us to calculate the transition parameters. Okay. So here certain things are there, we are not going to go too much into it. This is just what I said, free energy stabilization. So free energy against an outer parameter x, or can be it's like density or temperature. Then you here solid and melt, M is the melt. Then this here, this is stable phase, or S is stable and is metastable, is stable, and that lower free energy. Then at coexistence they are both same free energy, both are stable, but then when you lower the temperature or increase the density, then goes to the other things. And there are certain stability conditions of convexity and concavity, which I don't think I will have time for that, but basically once one says that if there is a maximum there, if I draw a line between this minima and this minima, then every point will lie above that chord. Okay. So these kind of things are maxima and minima, or if it is a minima here, I draw a line from here and there, then every point intervening lies below that chord. So that condition, simple condition, is kind of stated here, and that has certain consequences. And then another is that, for example, Gibbs potential is a concave function, and that means specificity is positive. Concave function again means the compressibility is positive, there is a negative sign in front of it. So on the other hand, Helmholtz potential is a concave function of temperature and convex function of volume, which is given here. These are the slides, I leave with it, and I will not have time to go through these details of that, but these are essentially fundamental things telling you stability of a system. But that does not fully answer the questions that I am after here.